Here's our position graph, velocity graph, acceleration graph. We're assuming we just have some object in motion. Since this is an x versus t graph, presumably we're talking about horizontal motion. So let's say this is just a depiction of a car moving back and forth. So this graph just represents the position of the car in terms of how far from the starting line. How far from the starting line it's going at any time. So presumably this represents the car starting at the starting line, moving forward, and then what's going on in this horizontal portion? What would that represent? If you've got a graph of position versus time, and you have a horizontal portion of the graph, what does that suggest?
It's staying in the same place.
Right, it's staying in the same place, right. The velocity is 0, it's not moving. So during this period of time, the car is just staying still. And then it starts moving again, going forward, forward, forward. And then what does this represent?
It's like you're going back towards the initial position.
Right, because as time passes, we're decreasing the x value. Decreasing position means going backwards, back towards the initial position. In fact, by this time, we reach the initial position again. So with that position graph representing just where the car is at any time, we should be able to draw a velocity graph, and then we should be able to use the velocity graph to draw the acceleration graph. And the position graph you can usually get from, like if you've got an experiment where you've got a moving object and let's say you've taken a video of it. You've got a perfect video of the motion of the object as time passes. If you were just watching this video, if you just play this video frame by frame, you can just note the position of the object at every instant in time. Maybe you've got a video of this object moving with a ruler behind it, just a meter stick or a measuring tape or whatever. You could just write down its position at every time as you watch the video, and then plot those points as a scatter plot on this graph. So as long as you've got video footage or some sort of record or where the object was at every instant in time, this graph is usually the easiest to start with. Alternatively, maybe you have a speedometer on the car. Maybe you aren't really watching where the car is, but you have record of its speedometer. Maybe its speedometer prints out information to a data table, so you know its velocity at every time. In that case, you'd start with the velocity graph and draw the others based on that. Or alternatively, acceleration. What has to be happening to cause acceleration? What makes acceleration happen?
A force?
A force, exactly. So if you know something about the force or forces acting on the object, you can often draw the acceleration graph first. So acceleration graph is a great place to start if you know something about the forces acting on the object. Just take all those forces, or the total force at every instant in time, divide by mass, and that tells you acceleration. So if you know the force at every instant in time, and you know the mass of the object, then you know the acceleration at every instant in time. So you can draw the acceleration graph and sort of work backwards to find the velocity graph and then the position graph. So in principle, you can start from any one of these three, depending on what information you have from the experiment, and then find the other two from that starting graph. Any questions on the general idea there so far? Then let's see if we can convert position to velocity. What's the relationship there? What is the relationship between position and velocity? Or what does velocity mean?
It's the derivative of position.
Exactly. Velocity is just the derivative of position. How fast position changes as time passes. So if we had a function for x, like if we knew an equation for that function, we could just take the derivative of the function. In this case, we don't have an equation. We don't have a formula for that function, but we do have the graph. And what does the derivative represent on the graph? The slope, exactly. The slope of position tells you the value of velocity. For example, in this first instance, in the very beginning, what do you notice about the slope of position in that region? In this short interval of time, what do you know about the slope? It's positive. And also, is the slope changing? No, during that first period of time, the slope is constant positive. So since during this first period of time, the position graph has a positive constant slope, that means during that first period of time, the velocity has to have a positive constant value. The velocity is just going to be a flat line for that short period of time. However, things change then. We go into a period of time when the position is constant. So what we need to do is treat this as a piecewise function. We're going to need to split this up into intervals of time where it's consistent during each interval. So if we're suddenly changing from a diagonal line to a flat line, that's a sudden change. So I'm going to mark that instant in time. And the nice thing about having these graphs stacked vertically like this, and this is generally how I would draw this every time, the position graph, velocity graph, acceleration graph stacked up vertically like this, because it makes it very easy to mark the same instant in time on all three graphs. If something important happens at some instant in time, you want to be able to keep track of that on all three graphs. Likewise, we have another important instant in time at this instant when it transitions from completely stopped to starts moving again. So I'm going to put a mark there at the instant when it starts up again. And I marked this point here because that's kind of important. Do you know what it's called at this point? What's going on here in the language of calculus?
I think it's called an inflection point.
Exactly. We've got an inflection point. It's transitioning from concave up curvature to concave down curvature. So that's something else important to look for. All those important points from calculus, the maxes and mins, the inflection points, look for those points and mark them because those are important instants in time as well. And then of course, this looks like an important point. That's when it hits a maximum. And then we keep going until it hits the starting point. And important things to look for are, if we're just drawing the velocity graph, we want to look for any regions, any intervals of time when the velocity is specific known values like 0, where the velocity is constant, where the velocity is positive, where the velocity is negative. For instance, we already saw during this first interval of time, the slope of the position graph is a positive constant. So that means the velocity's value has to be some positive constant. So velocity is just going to be a horizontal line at some positive value. But then what happens to the velocity in this interval of time?
It's just 0.
Yeah, velocity drops to 0 and stays 0 for that entire interval of time. What about in this period of time? What do you notice about the velocity from here to here? That is, what's the slope? What was that?
It's a linear increase.
We do have an increase, right? I don't know if it's necessarily going to be linear, but we definitely have, since the position graph itself is nonlinear, the velocity is definitely not a constant. It looks like we are going from, if we just start writing out information about the slope, like at this location, or at this time, I should say, the slope is 0. But what about up here? What's the slope?
Well, is it 0 or undefined? Because there's 2.
Yeah, technically it is kind of undefined because we're going from one type of function to a completely different type of function. But let's say right before that point, it looks like the slope is approaching what value?
0.
Yeah, slope is approaching 0. So that means if we want to make some marks on the graph here, the velocity graph, we know that at this instant in time, the position has slope 0, so velocity is going to be 0. At this instant in time, the slope pretty much becomes 0 and then kind of jumps to a different value. But we know it's at least going to be approaching 0. And in between, what do you notice about the slope at all these points in between?
It's increasing.
Yeah, we've got an well, is it increasing? The graph is increasing, which means the slope has what sort of value?
Positive.
Right. During that entire interval of time, we have a positive slope. So that means during that entire interval of time, velocity is going to be a positive value. But notice that it's a very small positive value, that is a very shallow positive slope, and then gets steeper, but then less steep. So we're going to hit a maximum velocity, at least a local maximum, at this inflection point, because that inflection point is where the position graph is at its steepest. It's only a little bit steep, then very steep, then less steep. So the velocity is going to hit a maximum here, probably less so than it is over here, because the tangent line, if I draw a tangent line here, that tangent line looks, is that as steep? Almost as steep as this. So that suggests that at that inflection point, at that instant, the velocity is almost as much as it was during this first period of time. Maybe something like this. In between, we're going from zero velocity to a higher velocity and then back down to a lower velocity. So we're going to have some shape like this. And because we've got this smooth curve here, I'm guessing this is going to be fairly smooth as well. Something like that. And it can be kind of difficult to tell exactly what it's going to be just from looking at the graph, but we at least know it's going to be a smooth curve that links these 3 points, because we're going from zero slope to a large positive slope back to almost zero slope. So I would expect this portion of the velocity graph to look like this. And then after that, what do you notice about the slope of the position graph in this interval?
It's a constant negative.
Right. We got a constant negative, and specifically a constant large negative, because this is very steep. So that means the velocity is going to be a constant large negative value. We're going to have velocity negative and very negative, so maybe way down here. So our velocity graph is going to look something like this. Any questions on that so far? And then we can do the same thing for the acceleration graph. If we want to draw the acceleration graph, acceleration is defined as what? What is acceleration? Yeah, acceleration is dv dt, the derivative of velocity. So that means we can take the exact same approach. In the same way that the value of velocity was just the slope of the position graph, we can also say that the value of the acceleration is the slope of the velocity graph. So if we can just make some notes about what the velocity graph's slope is on various intervals of time, that tells us everything we need to know about the value of the acceleration graph. For instance, in this interval of time, what do you know about the slope? Yeah, slope is 0. And same thing for this interval of time. So for both of these intervals of time, we're going to have 0 acceleration. 0 acceleration because velocity is not changing. And then in this interval, 0 acceleration because velocity is not changing. We got to be careful though, because we don't want to say there's no acceleration. We don't want to say there's no change in velocity, because what's happening at this instant? What's happening to the velocity at that instant in time?
There's like, it's 0 velocity versus like a constant.
Yeah, we're going from a constant to 0. That's a very sudden change. So if we try to actually find the slope at that instant in time, there is a change in velocity. Velocity is changing from some positive number to 0. So there's a negative value for a change in velocity. how much time does that change in velocity take? If we've got an instant drop from this positive value straight down to 0, how much time did that take? Or to put it in terms of slope, if you've got a vertical line, if the velocity is just dropping straight down, what's the slope of that vertical line?
It's undefined.
It's undefined because you'd have some change in velocity divided by no time at all. You can't divide by 0. You can't divide by no change in time. So the slope would be undefined. Or alternatively, we could say the slope is infinite, or maybe negative infinity because it's on its way down. But when that happens, if you have a velocity changing in 0 time, if the velocity instantly changes, that would suggest infinite acceleration. Is it possible to accelerate at an infinite rate? Or what would have to happen to make it accelerate at an infinite rate? What causes acceleration in the first place? Yeah, you got to apply a force, right? And in order to get infinite acceleration, you would need infinite force or 0 mass, but that doesn't really make sense either. So the thing is, in order to get an instantaneous change in velocity, you need an infinite amount of acceleration because you have 0 amount of time. And that means you need infinite amount of force. And there's no such thing as infinite amount of force. So that means this instantaneous change is impossible. Realistically, that's never going to happen. But why do we get that on the graph? Mathematically, why do we get this instant change in velocity on the graph? Why did we suddenly change from a positive velocity to 0 velocity? Where do we get those values in the first place? Like, why did we decide that there's a positive constant velocity here and a 0 velocity here? Yeah, we went back to the position graph, right? We had a positive slope for position, so we had a positive value for velocity. Then we had 0 slope for position, so we had 0 value for velocity. We get an instant change in velocity because we had an instant change in the slope. We had a sharp corner. In general, if you have a sharp corner shape on the position graph, you're going to get an instant change on the value of the velocity graph because you're getting an instant change in slope. And that suggests infinite acceleration at that instant in time. But that's not possible. That's not realistic. That's not realistic in terms of the actual physical world. Mathematically, it works. If you've got a sharp corner, then mathematically, yes, that is an instant change in the first derivative, and therefore it's an infinite second derivative or undefined second derivative. But realistically, we shouldn't expect that to happen ever. So instead, we can resolve that by saying, well, realistically, it probably wasn't an actual sharp corner. It was more of a very fast but not instantaneous curve. So let's round that corner out a little bit. Let's treat that as a very fast but not instantaneous change to the slope, which means this is going to be a very fast but not instantaneous change to the velocity. Maybe something like this. So this is more realistic. Mathematically, you can certainly have an instant change in velocity. But physically, that's never going to happen. Physically, we should expect it to be more realistic to have a very fast but not instantaneous change, a very steep diagonal, not a truly vertical line. And that means we can actually make sense of acceleration. What's the slope of this steep vertical line? Or this steep diagonal line, I should say.
A large negative value?
Yeah, this steep diagonal line has a very large negative slope, which means that acceleration during that short period of time has a very large negative value. During this short interval of time around that instant, we have a very large negative acceleration. So that means the acceleration is 0 while the velocity is constant, and then a very large negative for a very short amount of time while the velocity is changing, while we're rounding that corner on the graph, and then 0 again while the velocity is not changing. And strictly speaking, acceleration also doesn't instantly change. It's not like a force instantly turns on and instantly turns off. If you're pushing on an object, you're in the process of starting to apply that force and now full force and then starting to remove the force. It's not an instantaneous on-off. So realistically, the acceleration graph should also be a very fast but not instantaneous transition. So the acceleration graph should look more realistically something like that. You've got no acceleration because you're not applying any force, and then you suddenly apply a very strong force in the negative direction for a short amount of time, and then go back to no force at all. So a more realistic acceleration graph would look something like that. But mathematically, we might draw it as just a flat line and then a gap with a point, a single point down here, and then a flat line again. But this way would be more realistic, I think. Are there any other intervals of time where we know the acceleration is 0? Or any other instance when we know the acceleration is 0? Is there anywhere else or any when else, because we're talking about a time graph, any other time intervals? Yeah, when the velocity is a constant negative here. This last interval of time, velocity is constant value. So that means no slope at all. If the velocity has 0 slope, then the acceleration has 0 value. So the acceleration during this final instant in time is also going to be 0. Because we have slope equals 0 during that period of time. And what about during this period of time here? Is there any instant during this period of time when the velocity has 0 slope? At the very top, yeah. In calculus, if you're looking for a max or a min, you do so by setting the slope equal to 0, setting the derivative equal to 0, and looking for a single instant when the derivative is 0. So this is another important thing to look for. If you can find a max or a min, that single instant also has slope 0. So that means at that single instant in time, the acceleration is going to be 0. And then if we look before and after that, in this before interval, what do you notice about the slope of velocity here? Yeah, we've got a positive slope, which means during this interval of time, acceleration has to have a positive value. And then afterwards, we've got a negative slope. Negative slope means acceleration has to have a negative value. So that means we're going to have a positive value and then a negative value. But since this is smooth and continuous, we should expect the acceleration graph to be continuous as well. It's not just going to be a positive constant and a negative constant. Note that this starts off with a very flat. So we can treat that as increasing, but it has to get back down to 0 acceleration by the time we get to here. And then we dip into negative slope and therefore acceleration having a negative value. And then it kind of flattens out by the time we get to here. So we should get back to 0 again. So we should expect the acceleration graph to look something like this. With one other thing we need though. We have another sudden change in the velocity, which again, we shouldn't treat as instantaneous. If we want to be realistic, we should treat this as a curve rather than a very sharp, very sudden curve rather than a truly sharp corner. That's a very sudden decrease in slope. So that means we get a very sudden change, but not instantaneous change to the velocity. And we should treat that line, this sudden change, as having what sort of slope? What would you say
It's
about,
another like, it's another strong or high negative value.
yeah, this is another very large negative change, a very large decrease. So we should treat that as being a very large negative slope again. So again, it's going to be fairly continuous, and then a sudden drop down to a negative, and then jump back up. So it looks like our acceleration graph would look something like this. We've got no acceleration representing constant velocity and linear position graph, and then a sudden sudden negative acceleration representing a sudden drop in velocity, then zero acceleration representing constant velocity, and then positive acceleration representing an increasing velocity, dropping down to zero acceleration representing a maximum, a critical point in the velocity, then negative acceleration representing decreasing velocity, then a sudden strong negative acceleration representing a sudden decrease in velocity, then zero acceleration representing constant velocity. Any questions on that so far?
Yeah, so in general, when we're drawing these graphs, we should we always kind of artificially add in those like steep instead of the instantaneous transitions? Like, is it a good idea to kind of always have those?
To be realistic, I would say so, yeah. If you're given a graph that clearly has a sharp corner, you probably want to treat it as actually a sharp corner when you're drawing out the remaining graphs. But realistically, there are no sharp corners. If we look at an actual physical phenomenon, it's not going to have sharp corners like this. It's going to be very fast maybe, but not truly instantaneous transitions. You can't really have sudden jumps on the graph. If you have a sudden jump on the velocity graph, that means your velocity changed instantaneously, which means infinite acceleration, which would require infinite force. That doesn't really happen. You might have a very large force for a short amount of time, which means a very rapid change, but still not an instantaneous change. And likewise, you can't have a sudden jump in position. Objects don't teleport. You can't just have a discontinuity in a position graph. Realistically, we should expect all these graphs to be continuous and smooth. Any other questions on that so far? One other thing I want to look at here, specifically around this inflection point. An inflection point makes the difference between the graph being shaped like this versus the graph being shaped like this. And what do we call the distinction between those two types of shapes? The curving
concave
like
up,
this.
concave
What was that?
down, concave up and concave down.
Yeah, we've got a region where the position graph is concave up versus where it is concave down. And do you remember from calculus what makes the difference there? How would you find, in terms of calculus, regions where it's concave up versus concave down?
Did it have to do? Yeah, I think somebody, but like the second derivative is positive versus negative.
Right. And what's the second derivative of position?
Acceleration.
So if we take a look at the acceleration graph during those intervals of time, during this interval of time, we've got a positive acceleration. During this interval of time, we've got a negative acceleration. So if you've got an interval of time where the second derivative, the acceleration, is positive, you should expect the position graph, the function itself, to be concave up. If you've got an interval of time where the acceleration is negative, the position graph is concave down. And this also ties into the velocity graph. Positive acceleration means increasing velocity, means concave up position. Negative acceleration means decreasing velocity, which means the position graph is concave down. So everything you saw in calculus about first derivatives and second derivatives and functions and how they relate to each other, all of that still applies to position, velocity, acceleration, because velocity and acceleration are the first and second derivatives of position. So the velocity, the first derivative, tells you everything you need to know about the slope of position. The acceleration, the second derivative, tells you everything you need to know about the concavity and the inflection points. An inflection point is a maximum for the first derivative and is 0 for the second derivative. So those are useful things to look for. Look for maxima and minima, critical points, inflection points, where the graph is increasing versus decreasing, where the graph is concave up versus concave down. That's all useful information to tell you about the first derivative and second derivative. Any other questions on that so far?
I'm still a little bit confused when we like go down towards like the negative axis, or like when we stay on the positive or negative axis.
For which graph?
For like velocity, for example.
Like when we are positive versus negative values of velocity?
Yeah, yeah.
Well, the velocity always tells you the slope of the position graph. So a positive velocity means the position has positive slope. It's an increasing function. A negative value for velocity means the position is decreasing. It has negative slope. So for instance, in this entire time interval, there's only one interval of time, this last interval of time, where the position value is actually decreasing. So that's the only interval of time where the velocity has a negative value, because the position actually has negative slope during that period of time.
Oh, okay. Got it. Thank you.
Mm-hmm. On the other hand, if you take a look at this period of time, the velocity, the position graph is still increasing. It still has positive slope. It's that positive slope is getting weaker and weaker and weaker, but it is still positive. This graph the position graph still having positive slope means the velocity graph still has a positive value. It's just getting weaker and weaker and weaker, closer to zero. But the concave down of the position graph, and likewise the decrease of the velocity graph, means the acceleration graph does have a negative value during that period of time. Any other questions on that so far? All right, let's try another example working from acceleration backwards. Specifically, let's say we're talking about a falling object hitting the ground. And if we're dealing with a falling object, why would acceleration be a useful graph to start from?
Because we know that when doing a force diagram, that the force of gravity is the main thing acting on it. So acceleration is negative g.
Exactly. That falling object, gravity is the only major force acting on it. There might be some air resistance, but let's assume that's small enough to ignore. Force of gravity, mass times acceleration of gravity. Divide by mass, we just get acceleration is g, which let's round off to 10 meters per second squared. Or since it's in the downwards direction, and we're talking about acceleration as a scalar here. Technically it's a vector, but we're looking at a one-dimensional motion, just moving straight up and straight down. So we can treat downwards as the negative direction. Our graphs here are basically just looking at in this case, just the y component of acceleration, the y component of velocity, the y component of position. So the vectors themselves don't have a positive or negative sign, they have a direction. But the components, which is what we're actually graphing here, do have a positive or negative sign. So acceleration is going to be negative 10 meters per second squared. That's going to be a constant value as long as the object is just in free fall. So let's make our acceleration graph first. We want some more space here. And then we'll follow that with a velocity graph. One thing to keep in mind though, you often want to save some space here by not including values you're not going to need. Is this object moving both up and down, or just moving down, or just moving up? If we just take an object and release it from rest and let it fall, it's just moving down, right? Which means its velocity will always be what sort of value?
Negative.
Right, it's always going to have a negative velocity. If all it's doing is falling, if it's never moving up, if it's only moving down, its velocity will always be negative. So you can save some space here. Well, either save some space by not including a positive axis, or take up all the space you can and have a lot more detail. But I'm going to put the time axis all the way up here because I know I don't need to include any positive values of velocity. I only need to include negative values for v. Likewise for position, it kind of depends on where you put the axis. Where do you want to call x, or we're talking about vertical, so let's say y. Where do you want to call y equals 0? What would be a good height to call 0? If we're just talking about a falling object.
Well, you could either define it as like the initial point or the ground.
Yeah, we could call, those would probably be the two best locations to call y equals 0. Either the location is dropped from or ground level. And let's say for the moment that we're calling ground level y equals 0. Presumably the object's not going to go underground, so we can just treat 0 as the lowest it's going to get to. Which means for the height graph, the position graph, I don't need to include any negative values. So our height graph might look something like this. And we know the acceleration graph, important value there is going to be -10. And I am going to include a variety of values on the acceleration graph because there may be forces other than gravity that kick in later. But while it's in free fall, we should expect acceleration to just be this constant value at -10. So let's just assume that that lasts for a while. For a while, we have the object in free fall. So force of gravity is the only force, and the acceleration is just this constant -10. If that's the case, what does that tell us about the velocity graph? If we know the acceleration is -10, what does that tell us about the velocity graph? Yeah, it's going to have a slope. Specifically, its slope will be -10. And if its slope stays the same, if the slope is a constant -10, what sort of shape would we expect?
Linear.
Right, it's going to be a straight line. So the velocity graph is going to be a straight line with slope -10. Straight line with slope -10. One problem though, if all you know about is this, if all you know about a line is its slope, what don't you know?
Its speed, like its initial speed and stuff.
Right, we don't have an initial value. We don't have a, like in the classic example of a line y equals mx plus b, or mt plus b, because we're talking about time. We know the slope m, but we don't know the plus b. We're going to need one more data point. We're going to need one piece of information. As you said, usually the initial value. So let's say we do know the initial value here. If you're just, in this case, if you're just dropping the object, what's its initial speed? Yeah, if you just release the object, presumably from rest, it starts off at speed 0. But then it's going to have a constant negative slope, specifically slope -10. So it's going to be a straight line with slope -10. And that means we should be able to predict its speed at any instant in time. If we want to know how fast is it moving 5 seconds later, we can just go over 5 down 50, because that's slope -10. And after 5 seconds, its speed will be -50 meters per second. From that, we can also draw the position graph. If we want the position graph here, let's take a look at this in terms of derivatives. Actually, first, just conceptually, we know we start with 0 velocity. If the velocity is 0, what does that tell us about the position graph at that instant? The velocity graph just tells you the slope of position, right? If the velocity is 0, then the position graph has slope 0. If your graph has 0 as its derivative at just that instant, what sort of point are you looking at? What do you know about that point on the graph if the derivative is 0 at that instant?
it's like, oh, never mind. I was gonna say it's flat, but that's not necessarily true, right?
It is flat at that instant. And yeah, it may be a max or a min. If you're talking about derivative being 0 for a while, that's just going to be a flat line or horizontal line. If it's just 0, if the derivative is just 0 for an instant, that means at that instant the tangent line is flat, which means usually you've got a maximum or a minimum. If you've got a maximum, then the tangent line at that point is flat. Or likewise, if you've got a minimum, then the tangent line at that point is flat. This can also sometimes happen at something like an inflection point. It's possible to flatten out for that instant without reaching a max or a min. But the locations where, or the instance where the derivative is 0 are the places where you want to start looking for finding possible maxes and mins. And if we're dropping it, presumably that is from the maximum height. It's just going to fall from there. So we're going to have, presumably it starts off at the maximum. Slope is 0, so it starts off with a flat position graph, but then the slope becomes a little bit negative, so we get a little bit downwards sloping. And then the velocity gets more and more negative, so the position is going to have a steeper and steeper negative slope. So we should expect the position graph to look kind of like this. And specifically, what sort of shape does that resemble? What sort of graph do you expect there?
Like parabolic?
Yeah, this is going to be a parabola, or maybe you could say a portion of a parabola, because if the velocity graph is a straight line, and we're defining velocity as the derivative of position, how do you undo a derivative?
Take the integral.
Take the integral. Position is going to be integral of velocity. And in this case, velocity is just a straight line with slope -10, which we could write as -10t. The -10 can be pulled out, and we just get integral of t. What's the integral of t?
1/2 t squared.
Right. And because it's an indefinite integral, we also have a plus some constant. So we end up with y equals -5t squared plus a constant. And that constant ends up just being the initial height, because if you plug in 0 for t, you get y equals 0 plus that constant. So that constant is that height at time 0. And this also tells us that just knowing the velocity, once again, doesn't tell us a starting value for position. We're going to have to provide that separately. So we're going to have to say we already know, let's say we already know where this graph starts. Let's say we already have a y sub 0. We're going to get a downward opening parabola with its vertex at where it was dropped from, and then getting steeper and steeper because the velocity is becoming more and more negative. Of course, this only lasts until it hits the ground. Once it hits the ground, you're going to have to change things because the velocity rapidly goes up to 0, which means there's now going to be a large positive acceleration. So as soon as you hit the ground, things change. But during the free fall period, while it's just in free fall, while gravity is the only force acting on it, this is what these graphs are going to look like. A constant negative acceleration because of gravity, a straight line with negative slope for velocity because it has a negative acceleration. And if the velocity is linear, then the position is going to be a parabola. And this is generally true. In any situation where the acceleration is constant, the velocity will always be a linear function and the position will always be a quadratic function. Because when you integrate a constant, you get a linear function. When you integrate a linear function, you get a parabola, a quadratic. Any other questions on that? And if you want to get some more practice on this, you can get a lot of work out of just setting up 3 blank graphs, position, velocity, acceleration. Just draw some curve, whatever shape you want on one of them, any function you want, and then see if you can use that to draw the other 2 graphs. And try all 3 examples. Try starting with position and then drawing velocity and acceleration, starting with acceleration, drawing velocity and position, and also try starting with a velocity graph and then draw both the position graph and the acceleration graph from that. It's a good way to get some practice on both the position, velocity, acceleration stuff and some review of all the derivative and integral stuff from calculus. So give that a try. Email me if you have any questions or anything you want to work on, and I will see you at the final review session. You're welcome.
Thank you.